Before we get started today, I wanted to say a few words about yesterday's events. I know that the class is very poorly attended today, which is understandable, given that I'm sure that many people have been directly affected by yesterday's horrific events. We are going to continue with lectures as normal, but it's fortunate that actually we are broadcasting things to Singapore, because for people who miss the lectures, they'll be online, and so that it will be possible for them to catch up. And for people who need extra time, please talk with your recitation instructor if you require extra time to get this assignment in. I want to mention a couple of other things. One is that there's going to be a meeting of all MIT at 3 p.m. in Killian Court, where I'm not exactly sure what the nature of the activities will be there, but the Chancellor has called this meeting, and for everybody in classes will be canceled after 3 o'clock today. So people who have classes don't bother going because they won't be held. In addition, I think one of the best things that one can do if one has a personal stake in yesterday's tragedy is to give blood, because it is sorely needed. Usually blood supplies are very low, and blood does not keep very long. And so anybody who can give blood, I think that would be a very fine way to show the support for the people who've been directly affected by this tragedy. And at MIT today from noon to 6, and tomorrow from 10 to 4 in the Sala del Puerto Rico, you will be able to give blood. I had a close colleague, graduate student in our Theory of Computation group in the Lab for Computer Science, and the founder of Akamai Technologies, where I've worked for the last 2 days. He was on Flight 11, American Airlines Flight 11, which was the first flight to crash into the World Trade Center yesterday. And the mood at Akamai, where I visited yesterday, is very somber, okay, because he was, the heart and soul and leader of the startup company, and he will be sorely missed. I'm sure that other people have, being as we are so close to New York, other people have family, parents, brothers, sisters, mothers, and so forth. And so if you are directly affected, my condolences, and Eric's and the staff condolences to you and your family, or on the Pentagon tragedy as well. It's been a very, I think, tough day yesterday for everybody. Last night I had a problem session with the students in Singapore who are taking this class remotely, and they also, at the end of that session, personally wanted to convey their condolences to anybody who's affected by the tragedy. And so this is a time for pause. It is a time to think a bit philosophically and spiritually, if that is your bent, in order to to understand what's going on and how your role in education here at MIT is affected. My own view is that we do pause for such things, but we do go on. That is, what we're doing at MIT and what you're doing in getting an education at MIT, or as part of the SMA program in Singapore, is to improve this world, is to take your talents and make something positive of it. And when something as negative as happened yesterday happens, you can call into question what's the point of it all. But in some sense, all of you are the point of it all. Okay, everybody who has a has a positive character attribute whatsoever can understand that it's the improvement of this world that we're about. Okay? A lot of people go in and they say, what does the MIT education do for me? And indeed it does a lot for you, but it does, MIT gives to you so that you can give to the world. And although many of you say, well, but MIT takes a lot of money from me, or from my parents or whatever, okay, you should know that most of the cost of your education is not borne by tuition. Okay, most of the cost of the education is borne by the contributions by alumni, by the investments from the endowment, which is built up by contributions from alumni, by gifts from other people, and so forth. Okay, it's not borne by your tuition alone. In fact, I believe tuition is something like on the order of 40% of the cost of your education. And so, despite the fact that it feels very expensive at your end, it's also very expensive, you know, at the end of MIT. And it is, you know, I think at this kind of time, it's time to renew the commitment to do the best we can for each other. That means doing the best you can in your courses and so forth. Nevertheless, I think it is indeed worthwhile to take a little bit of time to pause, to reflect on people who may have been affected by this tragedy. I'm sure there's some people who don't even know whether their friends or family are alive or dead. It's really quite a horrific set of events, and you know, it's the kind of thing that when I was a child, we heard all about World War II, and we heard all about, and then we had the Vietnam War to contend with, and that was sort of our big moments of sort of learning to live in the world. And the last time that I remember something having this kind of impact was the Challenger disaster. I think even the bombing in Oklahoma City did not have this kind of impact overall in the community. And this is, you know, of course, compared to the Challenger disaster, is you know, is far, far worse. This is not just incompetence or something like that. This is some very malicious people with a lot of hate in their minds, being very organized, and it's really, really sad that such people are in this world. But this is the world we live in, and I think that, you know, personally, people can take a positive step. I think a great positive step is to go give blood. Okay, excellent positive step. Be part of this event. Don't let this event be outside of your experience. Okay, you've got to, when things happen like this, you have to embrace the event, as horrible as it may be. Okay, deciding that you're going to just turn your back on it is not an option, generally. Okay, because it will just build up. Okay, so find a way to embrace it. Find a way to appreciate it for the horrible thing that it is. And that's pretty much what I wanted to say, and then we'll move on to lecture. Okay, anybody want to make any comments? Okay, I'll be available, as will the others after class, if anybody wants to talk. Thank you.
Covered everything I wanted to say yesterday, except if you want to get counseling, there's lots of services available at MIT Health. So go there. It's a good thing. Don't feel embarrassed about it or whatever. And so we're here to do what we know and what we love and what we're here for, and that is to learn things and to have fun doing it. So let's go on and learn about algorithms. there any questions about course material from last class? We'll be talking a lot about recurrences again today, but now we'll be focusing on algorithms and a particular kind of algorithm called divide and conquer. So throughout the course, we'll learn several key paradigms for designing algorithms. So you're given a problem, you want to design the best algorithm for solving it. One way to do that is divide and conquer. We'll see lots of other paradigms in the future. And divide and conquer will be great for, in certain applications, making faster algorithms than what we currently have. Okay. You've seen a divide and conquer algorithm already. Merge sort is an example. But the general form, and I'll come back to merge sort. The general form is in 3 steps. So you have an algorithm that first divides your problem. So like in the sorting problem, really I have an instance of that problem. And you subdivide it into presumably smaller subproblems. And then your second task is to solve those subproblems, and that's the conquer step. So you conquer these subproblems in the obvious manner, just recursively. So divide and conquer algorithms are always recursive. And now you have solutions to each of these subproblems. You have to combine those solutions into a solution to your original problem. So the third step is combination. So that's the general form of a divide and conquer algorithm. There are lots of cases where it's useful. And one example we've seen, as I mentioned, is merge sort. So you remember the basic idea in merge sort is that you cut the array in half, you sort the 2 subarrays, and you merge the 2 subarrays. So let's just say that more carefully in terms of these 3 steps. The divide step, well, all you have to do is cut the array in half, which is just a conceptual thing. So there's actually no computation going on here. That's trivial. The interesting steps are step 2 and step 3. So to conquer, well, now we have these 2 subproblems, subarray 1 from 1 to n over 2, and subarray 2 from n over 2 plus 1 to n. And the conquer step is, well, you just recursively sort this subarray and recursively sort that subarray. And the last step is combination. And this is sort of where the most interesting thing happens in merge sort, right? This is just 2 recursive calls. And then combination is this linear time merge. So once these 2 lists are in sorted order, you want to look at the first elements. This was in the first lecture, so I'll just do it vaguely. You look at the first 2 elements, you take them in, you keep going. That gives you the entire sorted order. So this is the linear time merge of 2 sorted sequences. Good. Now we want to know how long this algorithm takes. And this is a recursive algorithm, so we're going to use a recurrence, just like from Monday. But I think we haven't actually analyzed this recurrence in class, so let's do it now. But instead of saying what the recurrence is, why don't I ask you, what is the recurrence for merge sort? have some t of n, which is the time to sort n numbers using this algorithm, how can we write it as a recurrence? Sure.
2t of n over 2 plus n.
Right. So it's t of n is 2 times t of n over 2 plus, could be n, but let's be safe and say order n, just to cover things, because there's some constants in here. Okay, now, as I sort of mentioned implicitly last class, now we can see it explicitly. These numbers all mean something in terms of the algorithm. Okay, 2 is the number of subproblems you're getting in the divide step. N over 2 is the size of each subproblem. And order n is, in this case, it's just how much time you're spending in the combine step. In general, both the divide and the combine parts are the non-recursive elements of the algorithm. And so this is the cost of dividing and combining. Okay, so that's the recurrence. And if we want to solve it, we can use the master method. So let me remind you of the statement of the master method, because it takes a while to memorize it. So there are 3 parts, 3 cases. First case was that f of n is big O of n to the log base b of a minus epsilon for some epsilon greater than 0, but I won't write that. And then the solution is, or sorry, I should probably write the recurrence as well. Let me be neat. I'll write this line again, so if you have room, you don't have to erase it. So the general form of the recurrence is you have a times t of n over b plus some function f of n. And then the first case was that f of n is big O of n to the log base b of a minus epsilon. And in that case, t of n is dominated by the n to the log base b of a. Second case is that f of n is roughly the same as n to the log base b of a. So up to a log to the k term. And k is at least 0. Again, I won't write all of the assumptions here. This is just for reference. And then we get an extra log factor. And finally, f of n is bigger than n to the log base b of a. So this is for some epsilon greater than 0. And we have a regularity condition. And here I'll write it so we don't forget. C is less than 1. Together, these two conditions imply that t of n is proportional to f of n. Okay, so that's the master theorem, and we'll use it a few times today, so I will leave this board up. And in particular, if we want to solve this recurrence for merge sort, let's go to another board. So for this recurrence, this is A, this is B, this is f of n. So we check, well, what's n to the log base b of a? That's what we need to compare f of n with. Well, here it's n to the log base 2 of 2, which is n. So that's n to the log base b of a. We compare it with f of n. Which case are we in? Second case, right? So we're in case 2. And so we know that t of n is basically f of n but with an extra log term. So here f is n, and so it's n log n, which, as you all know, is the running time of merge sort. So that's an easy way to analyze it. Now that was a very simple example. Let's look at a more interesting example. I think I'll go to a fresh board. So the next algorithm we'll talk about, you may also be familiar with. It's called binary search. So the problem we're interested in here is I give you a sorted array. It has a bunch of numbers in it, and I'm looking for a particular number. Find where it is in that array. How many people know the binary search algorithm? Okay, a little under half. Okay, so let me state the algorithm first in terms of these 3 steps, and then we'll look at an example. So it's a very nice algorithm. So I give you some sorted array. The divide step, sort of like merge sort, but instead of carving the array and looking recursively in the 2 parts, we'll say, well, let's look at the middle element here. So the divide step is to compare whatever we're looking for with the middle element of the array. So what are the outcomes of that? Well, the element we're looking for might be equal to this middle element. This is not drawn very central, but imagine this is the middle of the array. It could be that we found it. It could be this is the element we're looking for. Then we're done. It could be the element we're looking for is less than this number. Or it could be that the element we're looking for is bigger than this number. Well, both of those answers tell us something. If we know that the element we're looking for is smaller than this element, because all the numbers are sorted, that means our number has to be in this range. And otherwise, our number has to be in this range. So because it's sorted, comparing here, we get which half to look in. We can throw away the other half. So the conquer step, let's see what's the best way to state this. So conquer has to do a recursive call. And so we'll search recursively in one of the 2 halves. So one of the 2 subarrays. And then the combine step. Well, so we look recursively in the subarray. Either it finds it or it doesn't. Whether it's in that subarray is the same as whether it's in the total array by this argument. And so the combine step actually doesn't have to do anything. It just returns the same answer. Okay, so let's look at an example. Grab some numbers here. You humans are very bad at random number generation, so I will use my highly sophisticated source here. So there are 7 numbers And so in binary search, if we're looking for, let's say we want to find the number 9, which happens to be in there. Well, to look for 9, I'll start by looking in the middle element. So my first check will be here. And 9 is bigger than 8, and because this array is sorted, I know I have to be in this subarray. And so I recursively do a binary search in here. Binary search says, well, look at the middle element in your subarray. So that's the next number I look at. Well, 9 is less than 12, and so I should go to the left in the subarray, which means I want this subarray. Now there's only one element to look at, so in particular, the middle element is 9. So that's the third number I look at. And then I'm done, because that was the number I was looking for. If this were 10, then I would say, well, I couldn't find it. I ended up with an empty array. I didn't find the number. It's gone. But because it's 9, I say, yes, I'm done. Good. So that's the binary search algorithm, and we want to know how long it takes. What's its running time? So the first question is, well, this is a recursive algorithm, so we should give a recurrence for its running time, just like with merge sort. You may have already guessed the running time, but it's nice to be able to say, well, we can just use the master theorem, and immediately we get the answer. So for binary search, what is the recurrence for the running time for searching in n numbers? Sorted array of size n. How many how much time, how many comparisons will this algorithm use as a recurrence? Yep.
Tn over 2 plus theta 1.
Right. Tn over 2 plus theta 1. And so what is this saying? Again, we can analyze all the components. Implicitly, there's a 1 out here. And the 1 represents the number of subproblems. Here, when I divide my problem, I only got one thing to look in. And that's what makes this algorithm go fast. There's only one subproblem. Its size is n over 2. And this last term is the non-recursive component, and that's the dividing, which is just a single comparison, and the combining, which doesn't cost anything. Okay, but it's all at most a constant. So this is divide and combine. Okay, I won't write these anymore, but I just want to make it explicit. So now we need to know the answer. What is the solution to this recurrence? And so first we need to compute n to the log base b of a. What's that? I have to look at which is a and which is b, but they're vertically aligned, so it shouldn't be hard. 1? Right. Let me check. It should be 1. So we have log base 2 of 1. So it's n to the first power. No, just 1. N to the 0th power. Right, sorry. Log of 1 is always 0. Right? Good. So that's 1. So which case are we in? Second case, right. These are within a constant factor of each other. So this means we're in case 2. And k equals 0. The exponent in the log, there's no log term. And so t of n is, sorry? Log n, right. Everyone's saying log n. With the theta, of course. Right, because we just add on another log term. So that's the running time of binary search. That's cool. The normal searching algorithm is linear search. You just go through the elements one by one. But if you have a sorted array, you can do this binary search algorithm. It only takes logarithmic time instead of linear time, which is a big improvement. So that's sort of a very simple example of divide and conquer, because the division didn't act, I mean, you cut in the middle and you only got one piece left over. But it's powerful for getting these very fast algorithms. The next example we'll look at of a problem in a divide and conquer algorithm will be probably less familiar. So towards the end of this lecture, we'll get to more and more exciting material. So cooler algorithms. So the next problem is powering a number. So suppose I have some number a, say it's an integer, and I want to compute a to the power n. Well, the standard way to do that is you take a, you multiply it by a, you multiply it by a, you multiply it by a, you keep going. So that you can easily implement this as a for loop. So that takes n minus 1 multiplications, right? So the time here, let's say t of n. So we're parameterizing by the exponent. Well, that's going to be linear. But you think, OK, that's life. You've got to multiply n numbers. It's going to take linear time, right? It turns out you can actually do better than this. I thought the first time I saw this, I thought it was really cool. How many people have seen how to do better? So you're no longer excited. Oh, well, half of you, more than half have already seen this. Good. Well, how do you do better? Yeah?
If the power is even, you square the number that you're raising and have the exponent. And
Right.
if the exponent is odd, then you subtract 1 and multiply.
Right. So if the power is even, you square the number, and that gets rid of half of your exponent. So you divide n by 2. If it's odd, I'll write this down. So in general, if you want to compute a to the n, if your number n is even, it's pretty easy. You say, well, I know that this is a, let's see, a squared to the n over 2. Right? So I can rewrite that. Sorry, that's not exactly the form I wanted. Is a to the n over 2 squared, or in other words, times a to the n over 2. So if I recursively compute a to the n over 2 and then square that number, I get what I want. Okay, it's easy enough. If n is odd, it's a little trickier, but again, you gave the right answer. Now you can't take n over 2 because it's not an integer, but you can subtract 1 from n first, or just say n over 2 floored, and square that. So if I square this number, I get a to the n except for 1 power of a. Okay, because this is odd. I'm missing 1 power of a. I just multiply that on, and I get a to the n. So this is the key fact I'm using. And you can make a recursive algorithm based on this. And this falls into the divide and conquer paradigm. Good. So I should give this a name. So this is a divide and conquer algorithm. And it's called recursive squaring. Because for the most part, in each step, you're squaring the number that you had last time. Sometimes you multiply on an a, sometimes you don't. Good. So now we need a recurrence. So what's the recurrence for this algorithm? So you have to think, how does this fit into divide and conquer? Well, divide into subproblems. These are subproblems. Solve those recursively, then we have to merge, which is this equation is telling us how to combine the solutions to the subproblems. So what's the total running time as a recurrence? Yeah?
2 times t of n over 2 plus theta of n.
2 times t of n over 2 plus theta of n. That would be a little bit unfortunate because this is the merge sort recurrence, so we get n log n. And we already know how to get n. So I claim actually this algorithm is faster. That's an upper bound. That's right. Let's see. You're saying we have 2 subproblems, each of size n over 2, or each with value n over 2. And then there's this merge cost of theta n. How should I fix this? Make it a tighter bound. Yeah?
The merge cost is just theta 1.
The merge cost is just theta 1, right? Because what am I doing in the merge? Well, I suppose I already have the values recursively of a to the n over 2 or a to the floor of n over 2. And, well, I just square the number. That's one multiplication. Maybe multiply on another a. That's another multiplication. It's at most 2 multiplications in each step. So that's a constant merge cost. Let's see. Have we seen this recurrence yet? Sorry? Only one subproblem, right. This would actually be a linear cost. We'll see that later. But the other improvement to this bound is that there's only one subproblem. I mean, you can think of there being 2 subproblems, but they're the same subproblems, so you don't have to solve them twice. I just compute a to the n over 2 once. I can use that number twice. So that's why this is a faster algorithm. So only get 1 times t of n over 2 plus theta 1. Is that clear to everyone? No questions? Good. Well, we've seen this recurrence before, so we don't even have to apply the master theorem. It's theta log n. It's the same as binary search. So that, for the half of the people in the room who haven't seen this, that's very cool. I mean, that's a big improvement over normal multiply a by itself n times, which you learn in elementary school. So the next problem we're going to look at, you've probably seen the problem before, but I expect you haven't seen the solution because it's even cleverer than this one. But we'll see. I'll ask how many Fibonacci numbers is the next thing. So you want to compute Fibonacci numbers. How many people remember what Fibonacci numbers are? You should all know. Okay, this is, how many people can raise their hand? Okay, but just in case, or for memory or whatever, I'll write it slightly differently than usual. I'll write it as a recursive definition. So if n is small, let's say if n is 0 and if n is 1, well, then the nth Fibonacci number is just n. Okay? But if n is at least 2, and I fear I didn't leave enough space, let's see. Then you take the last 2 Fibonacci numbers, add them together. That's the nth Fibonacci number. So this gives you a sequence. See if I can remember it. Well, it's not very hard, right? So you start with 0, 1. This is F0 and F1. Then F2 is the sum of the previous 2. F3 is the sum of the previous 2. That's 2. Add these 2 up. That's 3. Add these 2 up. That's 5. Add these 2 up. That's 8. Add these 2. Starting to get to the limit of my addition capability. And then you say dot, 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 because that's your friend. And I get to stop. Okay, but that's an infinite sequence of numbers. It comes up in a lot of contexts, which you should have all seen in 604.2. The question is, how do you compute the nth Fibonacci number? Well, there's lots of algorithms for doing it. And so let me mention and I'm sure you know several algorithms for computing Fibonacci numbers, although you may not have thought of that in that context. You've probably even written a program to compute the nth Fibonacci number. It's like one of the first examples in programming courses. So what are some algorithms for this? Well, the naive algorithm is a recursive algorithm. Right? This is really naive, and probably you already know not to do this. I can say, well, that's a program in the appropriate language. It says if n is at most 1, then return n. Otherwise, return f of n minus 2 plus f of n minus 1. So that's from the definition, that's the obvious thing to do. And how long does it take? What's the running time of that algorithm? Yeah?
Theta of phi to the n, where phi is the golden ratio.
Big theta of phi to the n, where phi is the golden ratio. Sorry?
Stability of another algorithm. Is it a significant round-off error if we use the fact that...
We'll get to that. Yeah, good. Just wait a minute, OK? You're jumping ahead. You've been reading my lecture notes. So let's just say what the recursive algorithm is. Then we'll go to that algorithm, which is taking phi to the n, computing phi to the n. So the recursive algorithm, as it's described here, you get this big exponential tree. So the first thing you might say is, well, that's exponential time, and that's bad. And you even gave the exact running time. The base of the exponent is phi to the n, where phi is the golden ratio. And that should be 1 plus root 5 over 2. Good. OK. So that's a bad algorithm. That'll take a really long time. I tried all these algorithms in Maple yesterday with n equal 42, because 42 is the answer to the meaning of life, the universe, and everything. So it's a good number to try out. And I waited a few minutes, and this didn't finish. So that was no good. It would probably take hours to do 42, but I didn't let it go that long. But you were mentioning another fact, which is we know that the nth Fibonacci number, Fn, is actually very closely related to phi to the n. So it's phi to the n rounded to the nearest integer. Sorry, phi to the n divided by root 5. OK, if you remember this. If not, here it is again. And this you can also do with Maple, and you can say, how many people here use Maple or know how to use Maple? Mathematica? No? Just a few? OK. Like, what? MATLAB. Ah, good. Oh, zillions. Right. Sorry, I don't know the right keyword. I come from Waterloo, the home of Maple, and so I have to use Maple. I signed a contract. Well, anyway, all of these tools are very useful. You can do this with MATLAB, too. If you do it with MATLAB, you'll find the wrong answer. So I tried it with 42, standard floating point, and this is off by 1. Well, so that's kind of annoying. You're dealing with real numbers here. So you get round off. If you use floating point, it's not going to work so well. And so this isn't really an algorithm if we can't say whether it works, right? So, I mean, it's an algorithm, but it's not a correct algorithm. So that's not so good. In Maple, you can increase the precision and say, compute with 100 bits of precision, and then it gives the right answer. But you need to know how many bits of precision to use, and that's not an easy problem. A lot of people have studied that problem, but this is not such a good algorithm. I didn't say what the algorithm was. We can be sophisticated. Right? If we want to compute phi to the n, we can, oh, I've erased it already. We have this recursive squaring algorithm. Right? I don't have to compute phi to the n by multiplying phi by itself n times. I can do it or by calling it exponentiation routine in floating point. I can do recursive squaring. That's efficient. It would take log n time, but it's not correct. So that's no good. So repeated squaring, or recursive squaring. applied to phi to the n is fast but wrong. Okay, so we need a different algorithm. And let me leave the Fibonacci's numbers up. Presumably you know another algorithm for computing the Fibonacci numbers. Let's see. Think of anything that's faster than exponential and still correct. It's not very hard. Yeah?
You can build a table as you go so you don't recalculate.
Right, you can build a table as you go of all the fn's that you've already computed and reuse things. In fact, you don't even need a very big table. You just have to remember what the last two numbers were that you computed. So you just always keep f of n minus 2 and f of n minus 1. You add them up, that gives you the new number. You throw away the smallest. Now you've got the next two numbers to compute the next one. Okay, so this is called a bottom-up algorithm. And the idea we're using here is just to reuse all of our computations. Reuse the Fibonacci numbers. Once we've computed one, we don't have to recompute it. If you do the recursive algorithm, you do lots of extra work. And this way, you just do linear work. So I'm not going to analyze this algorithm formally, but it gives running time of theta n. So that's a big improvement over a recursive algorithm. You know, this runs in under a second on any machine for n equals 42. And the question is, can we do better? So that's a big improvement already, but you know, it's an exponential improvement from phi to the n to order n. And the really cool thing is that you can do another exponential improvement and get it down to log n. Okay? So, this shouldn't be obvious at this point. We need a new idea. And the idea is this theorem. Get it right. Suppose you look at the matrix 1, 1, 1, 0 and raise it to the nth power. It turns out, maybe some of you have seen this, that you get exactly the Fibonacci numbers. A triple of Fibonacci, consecutive triple of Fibonacci numbers. How many people have seen that theorem? Wow, half the class again. Good. So you all know how to prove it. I'll prove it again. But before we prove it, how should we design an algorithm based on that? Now we know this new fact. This is really a new way to compute Fibonacci numbers. I need to compute this thing. How should I do it? You've already answered a question. Anyone else? You.
The way you mentioned before, divide the problem in half.
The way I mentioned before, divide the problem in half. Yeah, and there's an even more specific suggestion. So we're going to use divide and conquer. We will use
Strasson's algorithm for multiplication.
Whoa, Strasson's algorithms for matrix multiplication. Somebody's been reading the text. That's cheating. We'll get there later. That will run faster. You're right, I think. It's not in by n. Oh. Yeah, Strasson's algorithm will still take linear time to do that, I guess. Right. So we'll get there. OK, another idea.
Can't you use that exponential squaring thing?
Yeah, exponential squaring. And just add some adds in there. Right. So the idea is, well, these are 2 by 2 matrices. OK, I take two by 2 matrices. I take a pair of 2 by 2 matrices. I know how to multiply them together. You do some multiplies, you do some adds. But now we can use recursive squaring, as we did before. Just treat these 2 by 2 matrices as single objects. I want to raise this thing, a, to the power n. So if n is even, I take it and I square it. If n is odd, I square it, and then I multiply another 1, 1, 1, 0 on. And each of those multiply operations will take constant time, because it's just a pair of 2 by 2 matrices. OK, so So we can apply this recursive squaring algorithm again, except now instead of dealing with numbers, we're dealing with matrices. But they're small matrices, so that won't hurt us. And recursive squaring, we know, takes logarithmic time. Theta log n time. Good. The theta is getting a little bigger, but it's all constant. Any questions about that algorithm? Well, for that algorithm to be correct, we have to prove the theorem. So let's do that. Okay. Any suggestions for those who haven't seen the theorem before, how to prove it? Got an n in there. Any suggestions, proof techniques? You had an idea? Induction. Good. That's all I wanted. These are easy questions, right? Think, well, I could use proof by contradiction. I could use, I don't know, nothing very exciting. I got an n. Why don't we induct? Induction is your friend. Use it. We'll use it all the time when it comes to algorithms, because especially when we have recursive algorithms. Okay, so we need a base case, and then we need an induction step. Base case, let's say n equals 1 to get started, because we have to look at f of n minus 1. So for that to be defined, n should be at least 1. Well, if n equals 1, then we can look at this matrix fn plus 1, fn, fn, fn minus 1, and cheat and use our quick reference table here and say, well, that's f1, which is, sorry, that's f2, which is 1, 1, 1, 0. Ah, that's exactly what we wanted. So if we take 1, 1, 1, 0, raise it to the first power, we get 1, 1, 1, 0. Okay, that's trivial. Then the induction step is, well, let's say n is at least 2. Now we want to look at the same matrix. Let's see. I think I'd actually like to do it in the other order. No, it's OK. You can do it in this order. So what I would like to talk about is this matrix, which is the same thing with all the indexes decremented by 1. Because this thing I know something about recursively. That falls into my induction hypothesis. So I need to write something here. But before I do that, to make it more intuitive, let's say, well, what I know about this matrix is that it's 1, 1, 1, 0 to the n minus first power by induction. That's what the theorem says. So I think, well, what I'd like to get is 1, 1, 1, 0 to the nth power. So I'd really like to say that's times 1, 1, 1, 0. And so why don't I put it up here? And now it's just a matter of checking that this equality holds. So you look, well, take these two numbers, multiply it like this. I add those up by the definition of Fibonacci numbers. That's f of n plus 1. And you keep going. Take this, multiply here. You just get fn, which is that one. Do this. Definition of Fibonacci numbers, fn. OK? This works out. And then we're done, because this is 1, 1, 1, 0 to the nth power. So that was easy. Induction is our friend. That proof would have been much harder any other way, I think. OK. Now you were suggesting Strasson's algorithm, so we're going to start moving towards there next, unless there are any questions about Fibonacci numbers. So this was two big steps from exponential time to to linear time to logarithmic time. And I think that's cool. So the next thing I want to talk about is matrix multiplication. And here we won't be talking about 2 by 2 matrices, but bigger matrices, n by n. Okay, so we're given 2 matrices. The input to the matrix multiplication problem is a matrix A and a matrix B. And the notation we'll use to say that has a bunch of elements is A sub ij. And B has elements called B sub ij. And I and j span from 1 to n. Okay, so these are n by n matrices. And our goal, the output of this problem, desired output, is to compute the product, C. So C should be A times B. And again, we'll use notation for its elements of C sub ij. And ij is also from 1 to n. So you all know the definition of a product of 2 matrices. The question is, how should you compute it? And there's a standard algorithm. Okay, why don't I write down the definition so we know what we want to compute? Because definitions help you make algorithms. So Cij should be a summation. You take one row of A, you take a column of B, you multiply them together. That gives you one element of C times ij. So let's say you sum k equals 1 to n. And you take row I of matrix A, and you multiply that by column J of matrix B. That's right. You take the dot product, so you add up all those products. That's the definition. And so that leads very naturally to an algorithm. Which I expect you've seen before. It's what's implemented in MATLAB and all those things. Oh dear. You know, there's stuff down here that hasn't been cleaned up in decades, I would expect. And I just added to the collection a chalkboard eraser. I'll fish it out later. Honest. Okay, what's the standard algorithm? I won't ask it because it's sort of hard to communicate code. It's just a triple for loop. So you say, well, I want to compute all of these numbers. So I'll just say, well, I goes from 1 to n, and then j goes from 1 to n. Those are all I want to compute all theCij's. Now to compute Cij, I should say, well, I want to add up those products. So Cij initially is 0, and then for k from 1 to n, this is just computing up the summation. I say add to Cij that product, Aik, Bkj. So it's a very simple algorithm. What's its running time? I've already answered. This should go instantly, yeah? N cubed, right. There's no recursion, straightforward. There's 3 loops from 1 to n. It's n cubed, right? This is just taking constant time. 1 multiply, 1 add. This is in a lower order term, n cubed. Now we'd like to do better than n cubed. And the topic of this class is divide and conquer. So let's use divide and conquer to do better on matrix multiplication. So the divide and conquer algorithm we need an idea of how to divide this matrix multiplication problem into subproblems. The idea that we'll use, we sort of want to carve up the input. The inputs are two matrices, n by n. So if we look at a matrix, you want to carve it up. It's two-dimensional, so let's carve it like a plus sign. So carve A and B. Instead of writing A and B, let me say we'll carve these n by n matrices. Let me draw the picture so you know what I'm doing. I have a matrix. Cut it in half both ways. So that what that gives us is a 2 by 2 matrix where each of the entries is an n over 2 by n over 2 matrix. We can call it a submatrix of the original one. Okay, so if I have my matrix A, I'll give these submatrices names because I need the names later. In fact, I would like to write A down here. And I'll need some space over here, so leave room for another one and another one. This is my product. I have C equals A times B. So I'll give each of these 12 entries a name. Just pick some letters. We don't like to use the letter I guess, so we jump from H to R. Good. Now we need... So that's sort of our subproblems. This is the divide step. And now we need to conquer these subproblems. So we need to compute R, and we need to compute S and T and U, and then together that will form C. So why don't I go up here. So what's R? What's R? A E plus B, yeah. I think you said it right. It's AE plus BG. Good. And I don't want to have to do this by hand, so I will cheat. All is right? Good. Now, this is sort of the wonder of matrices, right? These are not numbers. These are matrices. But this all works out. Even though A, B, C, and D are n over 2 by n over 2 submatrices, you can treat these just as if they were 2 by 2 matrices and write this, which is normal 2 by 2 matrix product. And it'll work. Now, what's going on here? Count up how many operations are going on. We have 8 multiplications. And these are multiplications of n over 2 by n over 2 submatrices. And additions, well, there's 4 of them. Okay, adding matrices is easy. You just add up every pair of terms. Multiplying them is not so easy. So this is really where everything is expensive. Multiplying matrices is what we're trying to do here. And so those are recursive subproblems. Okay, so do I want to write down think I won't explicitly say the divide and conquer algorithm here. To say it in words, you carve up the matrices like this. You compute these products recursively. Once you have those subproblem solutions, you add up like this, and that gives you C. So I'll write that down later. Question is, what is the running time? How can we write this as a recurrence? It's a recursive algorithm. We're doing 8. I'm giving it away. We're giving 8 subproblems of this size. What's T of n? Yep. Plus 4. Sounds good. 8 times T of n over 2. We have 8 subproblems. Each, the matrix size is n over 2 plus theta n. Okay, that's a little better. 4 was a little small. Let me just write what these are. So this is, again, the number of subproblems. So say sub-multiplications. And this is the size of the matrix, meaning one dimension of the submatrices. And who sees the bug with this recurrence? It's not quite right. Yeah? Should be n squared. Why? Right. Because we're adding matrices, they're n over 2 by n over 2, but that's roughly n by n. We have to add them up. They're n squared numbers to add up, theta n squared numbers to add up. It takes theta n squared time. So this is important. Increases the running time significantly. Okay, but it's only n squared because, remember, this is the cost of the division step and the combining step. The division is pretty easy. You just carve out the matrices. Recursion is straightforward. It gives this value. Then the key thing you have to do in the combination is to add up these matrices. And that addition is easy. And so that's where we're saved. Now the question is, what's the solution? So n, apply the master theorem. N to the log base b of a is, okay, now it's not quite vertically aligned, so you have to think, okay, 2 is b, 8 is a, log base 2 of 8 is 3, right? So n cubed. What case are we in? Speak louder. 1. I think that's right. Yeah. So now f of n is smaller than n to the log base b of a by a polynomial factor. So we're in case 1. And so what's our solution? Is theta of n cubed. It's just this, up to a constant. Okay, theta of n cubed. So is that a better algorithm than this one? Doesn't look so good. Oh, did I do something wrong? No, it's just, yeah.
Doesn't this algorithm only work on matrices of even dimension?
Okay, that's a good point. Throughout the lecture, I have been a little bit sloppy, and that's a technical term, in whether n is even. So when, well, okay, not all the time. But for example, when I analyzed the algorithm of recursive squaring, I said, well, there's a subproblem size is n over 2. But it actually was floor of n over 2. And I didn't write that down carefully. Merge sort, we were sort of assuming that each time we could split it in half when we wrote down the recurrence. So that's called sloppiness. And on Friday, you will see a way to cope with sloppiness. Sounds great for the office workplace, but it means a formal thing that when you're dealing with recurrences, you know, whether it's n over 2 or floor of n over 2, it doesn't really matter. Okay, you're right that I didn't specify the algorithm exactly when n was odd. And because you're recursing, I'm sort of assuming here that n is a power of 2, if you want to be careful. But it's pretty easy to fix this. So you just have to write floors and ceilings in the right place. You carve roughly in the middle in each row and roughly in the middle in the columns up to an additive 1. And then with the sloppiness method, you will see that the floors and ceilings don't matter much. Okay, but that's a good point to make. Other questions? Right, yeah.
Couldn't we just fill the matrices with zeros so to make them 2 to the n and we like them?
Okay, yeah, another thing you could do if you want to say, well, I like this algorithm. This algorithm is simpler, and I don't want to have to worry about when n is odd. So then you could say, well, I'll make the matrices a little bit bigger so that they're powers of 2, and then fill in the zeros. And that should work fine. So that's one way you could do it. That'll use a little bit more space, but it's all a constant factor. You wouldn't want to do that in practice, but theoretically, that's an easy way to make this algorithm right for any value of n. Okay, just add in extra zeros. Other questions? Good. Well, it wasn't so hot. So the point here is that divide and conquer doesn't always lead to a faster algorithm, just sometimes. And, well, sometimes you're lucky, sometimes you aren't. Here we weren't so lucky. But we don't give up that easily. We're going to go for a faster algorithm because we like speed, as Charles says. It's fun riding down your bicycle downhill at 30 miles an hour into a street. Okay. Speed is fun, so we want to go faster. And the faster thing we can do is called Strasson's algorithm. And at least how many people know Strasson's algorithm? At least one. 2. So this is who's been reading the textbook ahead of time. Okay. Just a couple. It's good. Don't want to have to repeat things. So the next few boards will be about Strasson's algorithm. And this is a very cool idea. I think it's still a little mysterious how Strasson came up with this idea. It's from the 70s, I believe, right? Like 76 or so? Somewhere around there? I forget. 69. Wow, 1969. So this is an old idea, but it was a breakthrough idea, and it still ripples through numerical analysis, I guess in particular. So the idea we're going to use is, well, that was one way to multiply 2 by 2 matrices, but there are other ways. I don't have to make those products and those adds. So what I'm going to do is multiply 2 by 2 matrices in fewer operations. Well, okay, this might seem like a little bit boring. Well, 2 by 2 matrices, constant time. But it's not constant time because the things that we're multiplying are not numbers, they're big matrices. Those are recursive calls. Now what matters here? We have 8 multiplications, 4 adds. As I said, the adds, they're cheap. We can do as many adds as we want as long as it's constant. We can do 42 adds if we want, and it won't affect the running time. The multiplications, they matter, right? 8 is the A term here. That's affecting the exponent directly. So if we can reduce 8 but increase 4, we'll be doing good. We'll be doing well. And Strasson's algorithm multiplies 2 by 2 matrices with only 7 multiplications. 7. How do you do 7? You cheat and you read your notes, or you go to the original Strasson's paper. It's very short. It's like 2 pages. And I'll just write this up. I don't know of any good intuition behind this. Feel free to let me know some. So each of these PIs is a product. There's some additions and some subtractions, but those, as we said, are negligible. It's the products that matter. And I need a couple of more. Okay, getting there. The last thing is I need to say what C is. I need to say what R and S and T and U are, just like I did before. And I'll do that in terms of these products. So that's 7 products. And now I just say, well, R is P5 plus P4 minus P2 plus P6, obviously. S, that one's easy. It's P1 plus P2. T is P3 plus P4. And U is P5 plus P1 minus P3 minus P7. Any questions? Gee. That's all you need to say. Well, you should probably prove that it works. It just takes some arithmetic. Let's do a little bit of it. Why don't I, in fact, erase this one? This takes a while to wrap your head around, but all you need is that you're computing the right things. So we're using cancellation, clearly. There's some minus signs in there. So the idea is that somehow we got away with only making 7 products. Because there were 8 things to multiply together. Didn't need all of them. So it's somewhat mysterious. Let's compute out one of them. Why don't you pick R or S or T or U? Pick a letter. S. S. Come on, that's too easy. Look, I can do that in my head. S is P1 plus P2. Some things cancel. The A times H cancels with A times H. That should be enough. Then we're just left with AF and BH. And I erased it, but that's what we wanted. Oh, dear, I erased it. Oh. You have notes, right? Okay, I'll write them down again. This would be a great time. I know a little bit of magic. This would be a great time to use sleight of hand. Change these definitions, making it look like an accident. Oh, I didn't really mean to erase those. I'll just rewrite them and write them differently. But no, you can check. You'll have notes. It's the same as what I wrote before. All right, S, we figured out was AF plus BH. AF plus BH. Good. Pick another letter. T. Come on. All right, I will pick R. Come on, T is too easy. You can do T in your head. All right, so we have P5. Oh, boy. Maybe I wanted to do T. You're being so nice. I mean, this is your chance to make me do work. But you realize my trick is that I will make you do the arithmetic. Plus P6. Okay. Well, let's just multiply it all out. AE plus AH plus DE is dH plus dG minus dE minus AH minus BH plus, last term, BG minus DG plus BH minus DH. Hopefully things cancel, because we only want AE plus BG. So these ones cancel. DGs cancel. Give me some more. AH. 1, 2, another. DH. Wow. BH. Good. That's fast. Parallel processing at its wonders. We're left with AE plus BG. And DEs, which cancel. Whew. That was close. Okay. Magic. Okay, I won't do the last two, but it's just as straightforward. And, well, we just leave it to Strassen to explain it all. Okay, are we nearing out of time?
Just finish up.
Okay, yeah, good. Ugh, it's stuck. Let me just write down this algorithm for you. Because I want to stress where we're using the 2x2 matrices. It's not just in the base case. It's all the time. So the divide step, we do two things. We partition A and B into n over 2 by n over 2 submatrices. And then we do some summations. Okay, in order to compute these products, we have to compute A plus B, F minus H, and so on. Okay, so using just plus and minus, we form the terms that need to be multiplied. Second thing, we conquer. Well, then we just recurse. We apply multiplication. There's 7 multiplications to do. You do them all recursively. Third thing is you combine them and you form C. And the last thing I need to do is the recurrence. We still have the master theorem up there. T of n is sort of like before, but now instead of having an 8, we have a 7. So we have 7 multiplications, each of matrices of n over 2 by n over 2. We have a whole bunch of additions. There are 18 additions and subtractions in the last step and the first step. All of that costs theta n squared. And then the question is, what's the solution? Well, we look at n to the log base b of a. Now we have n to the log base 2. I won't ask you to compute this in your head. That's around n to the 2.81. Which case are we in? One. It's a rather popular case. This is smaller, sorry, it's larger than n squared. F of n is smaller. And so the running time is this. T of n is theta of n to the 2.81. Well, maybe I'll write it formally as log 7. Wow. Faster than n cubed. You can do better. You can get down to n to the 2.376 or so. That's the best matrix multiplication algorithm on the market now. It's based on the same ideas. That's why divide and conquer is cool. See you next Wednesday. Monday's a student holiday, no classes.